Okay, good morning. Hope you all had a good weekend. Not sure where everybody is today.
There's a bunch of traffic over there by Sheffield.
Oh, was there? Okay. Okay, well,
House is on 40 and I just got here about it.
really? It was backed up on 1604? Yeah. Okay, well, we'll just wait then, I guess. No? We move on. Yeah, so let's get going. I have your quizzes. Well, let me wait until the end. Y'all just remind me. I have your quizzes. I don't want to pass them out until I get more people here. We're going to continue today in doing trigonometric substitution problems. I'd shown you 2 of the 3 trig subs. We're going to do one of the ones from last time, then we're going to do one that we haven't done, which involves when we have a plus underneath that root. So let's get started with this one here. So we want to find the antiderivative of the square root of x squared minus 25 all over x cubed dx. And I did end class last time with the problem. I think we had gotten it to like cosecant cubed, and I left it like that. So hopefully you had an opportunity to go take a look at that. I had done one just like it with secant cubed in the beginning of class, or previous class, so it worked out the same way. If you have any questions about that one, let me know. All right, so we're looking at this, trying to find the antiderivative, and it falls right into that first form there, where we have square root of a squared minus x squared. We know that the trig sub that we're going to use is x is equal to a sine theta, right? And so we just need to identify what a is for us here. So what's a? Oh, I'm sorry. Yes. Why did I write that down? I don't know. It's Monday, maybe? That's why? Square root x squared minus a squared. And then we have x equals a secant theta. My apologies. All right, but still, what is a? 5, right? So we're going to come over here and we're going to make a trig sub. I'm going to write it down what I'm doing. Do a trig sub. And a is 5 here for us. And the trig sub that I'm going to use is x is equal to a, which is 5 secant theta. Bless you. And now what was the next thing after I wrote that down? Take the derivative of this, right? So the derivative of this, dx is equal to 5. 5 comes for the ride. Derivative of secant theta is secant theta tangent theta d theta. Don't forget to put the d theta, right? And then I have to figure out what this square root thing turns into. So what does the square root of x squared minus 25 turn into? Well, if we're replacing our x with 5 secant theta, it turns into 5 secant theta squared minus 25. And the whole idea of this is that this should simplify to something where I can use a Pythagorean identity to clean it up real nice. So this becomes 25 secant squared theta minus 25. What now? Factor out of 25. You're left with secant squared theta minus 1. And that's the real key right here, this piece right here, that you get the secant squared theta minus 1, because what's that? Tangent squared theta, right? So this becomes, let me continue, I'll continue right up here. So this becomes equal to square root of 25 tangent squared theta by the Pythagorean identity. And now, since you have multiplication between these two, you can take the square root of each one. You get 5 tan theta. So that's the trigonometric substitution. We will replace any x we see with 5 secant theta. We'll replace the dx in the integral with 5 secant theta tangent theta d theta. And we'll replace this expression, if we see it, which we do, with 5 tangent theta. And now we just rewrite the problem. So integral, okay, the numerator is going to be this, 5 tan theta, over the denominator x cubed. So I have to cube this, don't I? I have to cube x. So I do 5 cubed 5 times 5 times 5, 125. And then secant cubed, secant cubed theta. And that's it?
Now we need
No. The dx, don't forget the dx, times another 5, and then secant theta, tangent theta, d theta. That's why you have to have the d theta there, because if you don't have d theta there, you're not using correct notation, but you're losing track of your variable, which may be a problem if you had to do like substitution after this. Any questions up to that? We're all good? You sure? All right, let's see what happens. I think this 5 and this 5 come together to be 5 squared, or 25, and then that reduces with this. That would leave me with a 5 down there, right? Okay, so I'm going to really just pull that 5 on the bottom out as a 1/5. And then, let's see, anything else kind of cancel out? I've got one of these secants goes away with one of those, so that's going to become squared. Also, I have on top tangent times tangent, tangent squared. So my numerator is tangent squared theta. My denominator is secant squared theta, d theta. We good? Now we have a trig integral. So we need to figure out how to evaluate this. Well, I know we've got tangents and secants, right, together, but they're not both in the numerator. Like we have tangents on top and we have secants on the bottom. The methods we learn for trig integrals when we have tangents and secants together is that they're both on the top. They're both in the numerator. So what I'm going to do is kind of a standard technique when we see something like this. I'm going to try and rewrite this in terms of sine and cosine. So I'm going to go here. This is 1/5 integral. Okay, this one right here, tangent squared. I know that's sine squared theta over cosine squared theta. And then over secant squared theta, which is 1 over cosine squared theta, d theta. That's just me rewriting in terms of sine and cosine. And then I have a fraction divided by another fraction, so I can flip this one up and cancel if possible. Do y'all see what cancels there? The cosine squareds, right? And so my new integral, which I'll come back over here, I'll need all the stuff I just erased in a second, but I'm trying to stay on camera. All right, so now we have 1/5 integral, and then the only thing left is sine squared theta, d theta, right? That's it. The cosines cancel when I reciprocate that. And that we can do because we've done it before, but just in remembering how to do this, we have a trig integral. We have sine raised to an even power. When we have sine to an even power, we use the, what do we do? Do we do Pythagorean or we do that other thing? The power reducing or the half angle identity, right? So what I'm going to do now is I'm going to rewrite this sine squared theta, remembering that that's 1/2 1 minus cosine 2 theta. That is an identity from pre-cal that we've already talked about, right? That's your half angle or your double angle, sorry, half angle or power. I call it the power reducing because you are getting rid of the power on sine, right? So power reducing formula. And so this should become, let's see, 1/5 integral to 1/2 parenthesis 1 minus cosine 2 theta and then d theta. Let's go ahead and pull the half out, and it hits the 5th and becomes the 1/10 integral. Let's see, 1 minus cosine 2 theta, d theta. And now I've got something very nice. I can integrate this and this separately, and I know how to do each of those, right? So let's continue. Continuing up here, let me go ahead and get rid of this. Okay, continuing there, we have 1/10, just leave it outside. And now I'm going to do the antiderivative of each of those and then plus c. So what is the antiderivative of 1? Theta, right? See, our variable's theta. So don't say x, right? It's not x, it's theta. Theta, and then now we take the antiderivative of this. That's, I think, last class or the class before we went through what happens here. You'll have to scale out. So what will it be? 1/2 sine 2 theta. Is it going to be plus or minus there in front? Minus, right? Minus. So if you take derivative of that right there, you should get cosine 2 theta, right? Because the 1/2 kills off the 2 that comes from the chain rule, and then you need the negative. That all right? Okay. 1/2 from the power? What power? Oh, no. No, because it's not raised to a power, we don't have to worry about that. I mean, because if you did, you would scale, no. Let me go back, I'll put it here. What I'm using here is this thing. I think this is what I put on the board. This right here. That's what I'm using, right? And so I'm scaling by 1/a. Okay. All right, no questions? We're not done, right? But we have an antiderivative. We just need to get it back in terms of x. Well, we need a connection between theta and x. This is where we usually use the reference triangle, all right? You sure no one has a question here? All right. Okay, this part's going to be weird. All right, going back to make the reference triangle, I'm going to use the trig sub that we made. So I'm getting ready to use my reference triangle, okay? I write down the trig sub I had, which was x is 5. It was secant theta, right? 5 secant theta. And then what I'm going to do is get the secant theta by itself. So I divide both sides by 5. And I've got secant theta right there. Right now, I'm just like brainlessly making a triangle. That's what I'm doing. I'm not even thinking about what's over here right now. I'm just going to make a triangle. Let's see, my right triangle looks like this. Here's theta. Here's the ratio. Now, secant is what over what in terms of like opposite, adjacent, hypotenuse? Secant's what? It's the reciprocal of cosine, right? What's cosine? Adjacent over hypotenuse, right? So secant should be hypotenuse over adjacent. So this x should be my hypotenuse, and this should be my adjacent on my right triangle. So my hypotenuse should be the x, and my adjacent side to the angle theta should be 5. And once I have two sides of a right triangle, I can always solve for the third, right? Are you all okay solving for this one? Can I just write what it is? You sure? Yes. Square root of what? X squared minus that squared, 25. So I had to solve for that. I didn't show the work. And the whole purpose of that triangle was that if I need any trig function of theta, I can now use this, right? If I need sine, I can get it. If I need cosine, tangent, cotangent, secant, cosecant, anything, right? What do I need? Sine of, 2 theta. This triangle is not a triangle based on 2 theta, is it? It's right. This triangle is based on theta. A 2 theta inside there does not mean you just like double the answer, right? We actually need another identity from pre-cal to turn this sine 2 theta into something that involves just theta. And that's your double angle identity from pre-cal. Very important identity. I'll put it over here because it's so important. Double angle identity. It says sine, on your formula sheet it says sine of 2x, right? Does anyone see it there? Sine of 2x equals 2 sine x cosine x. That's a formula from pre-cal. Okay, I know in my pre-cal classes I do stress that formula quite a bit, but pre-cal was like 2 classes ago. So, all right, so what I'm going to do here is I'm going to replace this right here. I'm going to replace this right here with that, 2 sine theta cosine theta. See how this formula allows me to talk about sine theta and cosine theta instead of sine of 2 theta. So when I rewrite this, I'm going to have 1/10 Okay, I'll get to the theta in a second. What happens here? I've got the half and the 2. Don't they just kill each other off? Right? So I'm left with just minus sine theta cosine theta plus some constant. And now I can use my triangle to get sine theta. I can use my triangle to get cosine theta, right? And I'll just slap those two things in here and multiply the two answers. But I still need to know what theta is, right? What theta is. And to get theta, I can't use the triangle. What I need to do is go back to this and do what? Take the inverse on well, sorry, not that one. This one. Take the inverse on both sides, all right? Take the inverse of the left. What's the inverse of secant? Secant inverse, right? So I'm going to do secant inverse on the left side. And then equals, when you do secant inverse with secant, they go away and you just get the theta, don't you? So I'm doing secant inverse on both sides. And that gives me an expression to replace theta with that is in terms of x. And I think at this step, I'll be pretty close to being done. 1/10, okay, theta we just said is secant inverse of x over 5 minus, okay, sine of theta, SOHCAHTOA. Sine is opposite over hypotenuse. So this over this. Times cosine theta. Cosine theta is adjacent over hypotenuse, 5 over x. Plus c. Now you could, if you want, multiply these together, which would mean you just plop a 5 in front of that root, and then x times x is x squared. But that's pretty much about all you need to do there. And then you could, if you want, you could pass the 1/10 through both, but I mean, I think this is good. This is all I really need. You've got the antiderivative in terms of x. Okay, what do y'all think of that problem? Only took us about 20 minutes. Pardon me? Yeah, so I really like this problem. Yes?
So with these problems, like in the original, it had the square root of x squared minus 25.
Yes.
Is that always going to, is like the original square root expression, is that always going to play a part in the reference triangle?
Yes. Yes, it will always be part of the reference triangle.
Okay.
Well, I think I said last time 97% of the time. Yes, there are some exceptions. It depends on how you simplify things. And I might get to an example where you see that here in just a minute.
Okay.
So why do I like this problem? Okay, well, first you have to know what trig sub to make, which I almost screwed up in the beginning, didn't I? Right? You have to make the right trig sub. And then once you simplify everything, you looked at your trig integral, you needed to know to get it in terms of sine and cosine. When you got there, you had to realize sine was an even power, so you had to use that power reducing formula. Once you use the power reducing formula, then you realize, oh crap, now I'm talking about sine 2 theta, so then you had to use a pre-cal formula to get you back in terms of just theta. And of course, you have to make a reference triangle. I mean, this is like so many different ideas in one, right? And so I can pretty much guarantee you 100% that you're going to see a problem where you do the trig sub, and what you wind up getting is either like a cosine squared or a sine squared. I'm saying on a test, right? And then you'll have to do the power reducing, and every single time you ever do the power reducing, this is going to become, well, when you do the, I've already erased it. Every time you do the power reducing, it turns into a cosine 2 theta. And then when you integrate that, you're going to have sine 2 theta, so you're going to need that double angle identity. I'm promising you that on the test, okay? So be prepared for it. All right, I have like 5 or 6 examples. Yes?
The double angle formula, is that on a formula?
Yes, it is. It's on it's on the trig, I think it's on the trig page.
Yeah, reference page 2.
Reference page 2, it's on the bottom right-hand corner.
Yeah, right next to the
Above
Yeah.
the half angle.
Above half angle, yes.
Could you plug the arc secant to where it says sine 2 theta to replace the theta?
Okay, so yes and no. Okay, yes and no. So what I'm being asked is, can you just solve for theta here, right? Just solve for theta, like this. and then plug that answer in right here. And then instead of doing the double angle identity, just your answer would say 1/2 sine of 2 times, and then next to it, secant inverse of x over 5. That, I would say yes, all right? That is correct, and that's what probably a computer is going to give you as well, all right? But you circumvent the reference triangle idea, which I think is there's a bigger reason for this reference triangle. It's not that I'm just trying to torture you, it's that this idea of a reference triangle comes up not just here, but in other classes as well. So if you continue to avoid it, at some point you're going to need it, all right? And so I just want you to get used to the idea. So on a test, if you do that, I'm not going to count it wrong, but I'll probably just kind of grin a little bit and go, they're avoiding the reference triangle, all right? And it might actually, there might be a problem where it doesn't work. So, yes? Questions? All right, let's do another one. So what we haven't done, right? What we haven't done is one with a plus, right? We haven't done one with a plus. See if that comes back. There we go. We have not made that trig sub of a tan theta yet, right? So let's do one of those. By the way, we are officially a little bit behind now. Today we are supposed to start partial fraction decomposition. And this is just the nature of Cal 2. Okay, it's really difficult in Cal 2 to stay on track, stay on pace here. All right, it's really hard. So I'm aware we're a little behind. We'll just keep going. We might come in maybe over, what is it? We have Thanksgiving. Do we have Thanksgiving break? No, we don't. We don't have Thanksgiving, right? I mean, there is a Thanksgiving break, but it doesn't impact us, right? Yeah, so no, maybe we'll just come in on the weekend one of these days, right? No? Okay. All right, so how about this one? X cubed square root of x squared plus 4 dx. So I picked these problems before class because they all have something in them that I like, that I want you to see, all right? Now, I will say that this problem actually may go with the basic U sub. It might. My first instinct on this would be to try a basic U sub. U would be x squared plus 4, and then I'd turn that into x times x squared. And I bet you it would work. But again, I'm going to avoid that because I just want us to get through some more trig sub. Just so you know, that's x cubed, right, times, that's not a cube root on that. All right, so my trig sub, right? Trig sub. Everybody see it? X squared plus a squared, right? A for us is 2, so a is 2. And the trig sub I'm going to make is x is a tan theta, so 2 tangent theta. Because I have a plus here, right? And now I'm going to differentiate that, right? So derivative of this would be 2, what's derivative of tangent? Secant square. Oh, you're doing antiderivative, careful. Derivative of tangent is secant squared theta d theta. And now I also want to go figure out what does that square root of x squared plus 4 turn into. This should turn into something nice. So what is x squared for us? Let's see if I can just write it down without putting it like something squared. What is this squared? 4 tan squared theta plus 4, right? So all I did was replace the x with that, squared it, and put it here. And we should be able to factor out a 4 from each of those. Yep, 4, and then that will become tangent squared theta plus 1. And that part right there, again, is a trig identity. That's secant squared theta. So this is the square root of 4 secant squared theta, which is just 2 secant theta. All right. So by making this trig sub, I'll replace all my x's with 2 tan theta. I'll replace dx with 2 secant squared theta d theta. And the square root piece there is going to turn into 2 secant theta. And now I'm just going to rewrite the problem. I think I can just do it right here. All right, x cubed is the first piece, right? X cubed. So I've got to cube this. 2 times 2 times 2, 8. And then tangent cubed, theta, times. Okay, so that's x cubed, right? Now, the square root of all that crap right there. Well, that we said was 2 secant theta. Am I done? No. Times, don't forget dx, right? dx, that's one of the big things students forget. They forget dx, and then this right here, they start working with it, and they can never figure out what it is because the problem was made so it would work, but you forgot dx, and now it's not going to work, okay? So dx, dx is 2 secant squared theta d theta. I should mention that these problems have to be made very carefully. I can't just like throw a random problem up here, just make up my own, because I'm not sure how it's going to work out. So I have to be careful to make sure I use like a book, like problem from a book, that it can be worked out, right? All right, so we move on. Let's pull all those constants out. What do I have on the outside of this thing? 32? 8 times 2 times 2? 32 on the outside? Okay, how many secants? How many? Doesn't matter what order. Let's go tangents first. We have tangent cubed theta, right? And then secant cubed theta, d theta. Okay, so I've got secants and tangents together, but see, they're not a ratio like the last problem. So I'm not thinking let's go sine and cosine like I was the last one. Here they're together, right? So now I go back to last class. I'll scroll up. What do we do when we see tangent and secant together? Let's see, if the power, so I'm looking at those notes that you're allowed to have on the test, how to integrate powers of tangent and secant. If the power of secant is even, is that even? No. Okay, move on to part 2. If the power of tangent is odd, is the power of tangent odd? Yes, so what it says is we're going to try and pull out a factor of secant x, tangent x. So I'm going to peel one tangent to the side, one secant to the side. Let's do it. 32. Okay, I'm going to peel one of those tangents off, so I'll have tangent squared theta. I'm going to peel one of those secants off. I'm going to have secant squared theta. And then next to it, I'm going to put the tangent and the secant that I peeled. And I'm going to write it this way. Secant theta, tangent theta, d theta. And the whole idea here is for us to recognize that this right here is going to be our du. That's going to be the derivative of the u that we're going to make for our substitution. So what do you take the derivative of to get this? Secant, right? Secant. So remember, this is where I was saying, like, I'm sitting here thinking to myself, right? Like, what's u? U is going to be secant theta, right? U should be secant theta so that the derivative of it's right here. That means I need this entire integral in terms of secant. This already is in terms of secant. Tangent squared can get switched to secant using the Pythagorean identity, can't it? Okay, so this becomes 32 integral. What is tangent squared theta in terms of secant? Secant squared theta minus 1. That's using the Pythagorean identity that's on your formula sheets and solving it for tangent squared. And then, so that's this, and then we have secant squared theta, and then secant theta, tangent theta, d theta. Now don't lose sight of what you're doing here, right? You know that this piece right here is du. And u is secant theta, right? So right now, don't go distributing this through. Like right here at this point, just replace secant theta with u, right? Make your basic u sub, right? This is a u sub now. I'm going to let u be secant theta. Du will be secant theta, tangent theta, d theta. And now I rewrite it. So this integral becomes 32 integral. All right, what does this turn into? U squared minus 1 times u squared times du. U squared minus 1 times u squared du. Now, distribute u to the fourth minus u squared du. And now that's just a polynomial. We can find the antiderivative of that by just power rule. So 32, well, I better do it below this. So 32, okay, I'm actually taking the antiderivative now, so no more integral sign. 1/5 u to the fifth minus 1/3 u to the third plus c. What was u? Secant theta. Okay, so coming up here now. Let's get rid of that. So we have 32. Okay, 1/5 u to the fifth, but u was secant. So I'm going to put secant to the fifth theta minus 1/3 secant cubed theta plus c. Now what? Are we done? Nope, we got to get it back to x, right? We're still not in terms of x. So now I'm going to go to the trig sub I made. The trig sub I made was, x was, I forgot, 2 tan theta? No, 2 secant theta, right? 2 secant theta. Right? No, it was tangent. I'm getting confused. Yeah, that was a derivative. Okay, 2 tan theta. That was our basic u sub. I'm sorry, that was our trig sub, damn it. All right, divide both sides by 2. All right, tangent theta is x over 2. And now a reference triangle. And for this reference triangle, tangent is opposite over adjacent, right? So this is x and this is 2. And if you solve for this side, you will in fact get that square root x squared plus 4 that we were thinking we would probably see 97% of the time, right? Yeah. All right, I think we're ready to put this together. Our final answer over here, 32. Okay, 1/5